Hey everybody, just want to talk to you today about the proper order of operations for figuring out the values in a series circuit. In this case, we've got our ET, our total voltage already established for us. So I'm going to write that out first before we even get started. I've got ET established at 100 volts. Going to be pretty common in our lessons, both in LMS and in class, for voltage to already be established, total voltage to already be established. It's not necessary that they're always, not necessarily always going to be true, but oftentimes going to be true. Now that that's established, our order of operations has got to be pretty rigid the way that we go about this. I don't want to be skipping around steps, so I'm going to go about this in kind of the exact way that we should be going about our order of ops for series circuits. And next order of operations for us would be figuring out the other total values for this circuit, specifically starting with our RT. We've got to start with the RT here. We don't have any values written in for our R1, R2, and R3 individual resistors or loads, if you will, so we're going to write them in ourselves. Let's go ahead and call R1 50 ohms. We'll call R2 100 ohms. And we'll call R3 75 ohms. We may remember that in series circuits, it's a pretty simple formula for figuring out what our total resistance is when you have all the values established for your individual resistors. And you may also notice over here that I've got this laid out a little bit strange. I've got this going from left to right, basically. I don't know if you can see what's happening there, but I've got my negative terminal over here. I've got my positive terminal over here. This is going to be a pretty similar layout to what we're going to try to rewrite our circuits as going forward in this term, including the color coordination of each of these here. We can call them legs if you want to of the circuit, or they're kind of analogous to actual conductors in the field. Like I've got my conductor going from the load side of my source to the line side of this load, and then I've got another conductor going from the load side of this resistor to the line side of the next one, and so on and so forth. Not super handy right now in series circuits, but it's going to be very helpful for us when we get to parallel circuits and combo circuits. For now, just rewriting these in color coordinating way to establish what each of these conductors, if you want to call them that, would be, is just going to be a good habit to get into. Similarly with this left to right format, just going to help us order our thoughts, order our components, and help us figure out our values a little easier. So transferring that from this circuit style to kind of unraveling it basically out into a straight line, the first thing I'm going to come across is my R1 in the circuit at 50 ohms. Again, this is going to be a pretty common way that we'll rewrite our circuits going forward. R2 is going to be 100 ohm, and R3 75 ohm. And then we'll use the formula we said before of RT equaling R1 plus R2 plus R3, 50 plus 100 plus 75 ohms. We end up with 225 ohms. Now that I have that established, the next total value I want to figure out is my current. And just using Ohm's law, I know that if I got ET and RT, E total and R total, I can figure out what my IT is. That's just a simple first circle formula. Equals I times R, or if we're solving for I equals E over R. So that would be 100 volts over 225 ohms. I end up with 0.44 repeating amps. Now, if I were to keep going all the way down, 0.444444, and so on and so forth, I would get my most accurate number at the end of this thing. And when we're doing all our circuit calculations, it's really important for us to leave as many as we can in here until the very last step we can tidy it up. But as far as you can go to the right of this decimal as you're doing your initial calculations, the more accurate you're going to get. We'll see an example of that in a second. I'm going to leave this here at the 0.44, and it'll show us at the end how that can throw us off a little bit in our numbers, but it's close enough for now. So I've got my 0.44 amps. If we remember from class or the LMS, our formula for figuring out our current is IT equals I1 equals I2 equals ... IN, right? This is just saying that my current's the same everywhere in a series circuit. My current here, IT, for the total circuit, is going to be the same as R1. So I've got my I1 would also equal 0.44 amps. And same for R2, or I2 for current, 0.44 amps. And same for I3, 0.44 amps. Because current only has one, basically, way to get through all of this. It's only got one path to get through all of these. It's got to travel through everything, so it's not going to change. It's not going to fluctuate if it's only got one path to go through there. This is an important pause to state that at this stage of any circuit that you're rewriting, series, parallel, or combo, if you have two values at any given load, as we do at this stage, I can figure out any third value there, which is, I think, really handy for us to know going forward. We've got a lot of processes that happen later on down the road, especially in combo circuits, and it can be easy for us to do a bunch of extra steps that we maybe don't have to necessarily do. And I want to make sure that we understand that if I have two values here, I can figure out any third value. In this case, let's go ahead and figure out what our voltage dropped across each of these is. And I want to make sure we understand we're not talking about voltage drop as if we're trying to figure out the resistance of using the resistance of a long conductor or anything like that. That's not what we're talking about here. We're not talking about 3%, anything like that. We're talking about the voltage that's kind of essentially subtracted in a series circuit at each one of these loads. We might remember Kirchhoff's law says that if I start out at 100 volts, I should basically be subtracting a certain voltage at each of these, however many there are, to that where I get to the end, I should have 0 volts left. So we're going to check our work here and use some Ohm's law to figure out whether we've got our numbers correct on this. So what we're going to do here, R1, we're going to use Ohm's law to figure out what my E1 is, my voltage here. And that's pretty simple, right? If I've got an R of 50 ohms and I've got an I of 0.44 amps, I know that E equals I times R. And so I'm going to type that in, and I end up with 22 volts dropped here at R1. I'm no genius mathematician or anything, but I know if I've got 50 here and I've got 100 here, then that means I've got twice that amount down here. So my E2 is 44 volts dropped at R2. And my E3, I'll do some math on that one here. We'll figure out that I end up with 33 volts dropped there. Now you may notice here that I've got 22 plus 44 plus 33 means I've got 99 volts. 100 minus 99 means I end up with 1 volt back here instead of 0. Kirchhoff's law said I should have 0 volts back here. But again, we remember that I rounded pretty heavily on this one. If I would have kept all those extra 4s in to the right of that, I'd be coming a lot closer to 0. And then Kirchhoff's law would say everything is just fine. That's about all I wanted to cover there. Really, really crucial though, order of operations to reiterate here is that we want to make sure, again, assuming our total voltage has already been established, we want to make sure we don't skip our steps and do RT next, IT after that, our total resistance, and then our total current. Our total current is also the same as at each of these individual components. And then once I've got two values established at any individual component, I can figure out any third value. And that's all I want to talk about today. If you have any questions, go ahead and email any of the instructors. We'll be happy to walk through it with you. Otherwise, I'll just see you back at class. Thank you.